Adam, and we're going to start off with a little bit with radiation. Back in 1896 or so, a guy named Henry Becquerel was looking at rocks. You guys ever been in cathedral caverns? They got those rocks in there that if you shine lights on them and then you turn off all the lights, what happens to the rocks? They glow. And that's what Becquerel was trying to figure out, was why were rocks doing that? Studying those rocks, and eventually one day he put one of those rocks in like a drawer in his desk by accident, just stuck it in the drawer to keep it there, and there happened to be some film laying in the desk, like sheet film. Set the rock on top of it. A few days later, he develops the film. And what does he see on the film? The rock. He can take a picture of the rock, but there's a picture of the rock on the film. So Becquerel figures out that rock is giving off something. And that's our first inkling of the existence of radiation, was this rock. It's a picture of this rock that happened by accident. So Becquerel was friends with the Curies. Together, they started studying, what radiation was. I think all three of them died of radiation poisoning eventually, one way or another. No, they just didn't know what it was. They didn't realize it was dangerous. Ernest Rutherford comes along a little bit later. And Rutherford takes, and I'll show you a picture of this in a minute, but he basically takes a lead box, puts a radioactive element inside that lead box, bores a tiny hole in it, so it's basically like a radiation gun, shooting out a beam of radiation through the little hole. So it's made out of lead, so it can't come out anywhere else, at least not very much, except through the hole. And then that beam he shoots out through a magnetic field. And what does he see? What's he able to sense after the beam goes through the magnetic field? What happens to it as it goes through the magnetic field? It separates, and it separates into three things. It separates into what we now call alpha particles, beta particles, and gamma rays. The alpha particles, you guys, I'm sure have heard of alpha particles before, one place or another. They're actually pretty much equivalent to the nucleus of a helium atom, which means we can write them like this. Sometimes you see He here, sometimes you see that. That's just an alpha, right? What does that mean it's made out of? What does that symbol tell us? The 2 and the 4 tell us. Yeah, the 2 tells us what? 2 protons, and the 4 tells us 2 protons in addition to 2 neutrons. So it's the same as a helium minus what? Minus the electrons, so no electrons there. Shot out at high speeds, but it's positively charged because of those 2 protons. The beta particles, people were eventually able to figure out that they're just beams of electrons getting shot out. Negatively charged particles. So we might see the beta particle written like this. So again, it's a beam of high-speed electrons. That's supposed to be a beta. Looks kind of like a beam. And then a gamma particle is essentially just light. High-energy light, what we might call photons. What's a photon? Yeah, but a photon is like the smallest packet of light you can get, right? It's like a piece of light. It's almost like a particle of light. Not a proton, a photon. The symbol for a gamma is 0, 0, letting you know what? It's not matter. It's energy. It's light. And a gamma sort of looks like a Y, a little bit like a Y. So let's look at a picture of what Rutherford actually saw. This is kind of what he did. So he's got his lead box. He's got his radioactive material in here. Got a hole. He's shooting out this beam. Goes through a magnetic field, or in this case, electrically charged plates. Either way would work. So if it's an electrically charged field, the beta rays get attracted toward the positive, because they're, what do we say betas are? They're right there, electrons, so they get pulled that way. The alphas rather, are positively charged things because of the protons. They get pulled down this way. The gammas go straight through because they're not charged at all. And he's able to sense that on a piece of film, essentially, a photographic plate on the other side. So he sees 3 splotches. essentially. Does that make sense? Come on in, guys. All right, another thing we want to talk about is what scientists thought about the atom. One of the first atomic models was called the plum pudding model. And that was pretty much formulated by a guy named J.J. Thomson. What Thomson thought is that the atom was this big hunk of solid, positively charged stuff. That's everything in pink. And that embedded in that pudding of positive charge were little negative charges, like a raisins or something. So there were these little negative raisins in this big positive plum pudding thing. But the sense was it was a solid hunk of matter. Most of the matter was positive with little negative chunks, but essentially Thomson thought the atom was a solid thing. That was the model that was around for a pretty long time. But again, along comes Rutherford, pretty important scientist. In 1911, he did what we call the gold foil experiment. Everybody's heard of the gold foil experiment before, right? Again, he's shooting beams of particles. This time he's shooting beams of alpha particles at thin sheets of gold atoms. And what he expected to happen, as the alpha particles got near the atoms or went through them, he expected them to get deflected just a little bit and get moved over to the side because of the positive nature of the atom. He didn't expect the deflections to be too big because not only in the atom were there positive charges, there were also what? Negative. So he expected just small deflections. But what he got surprised him. In most cases, he got no deflection. Most of the time, what happened to the particles? They went straight through. That really surprised him. When there was a deflection, it was like it had hit something huge. It bounced off crazy to the side. So Rutherford, let's go to his experiment here first. Here's what his experiment looked like. So again, he's got his lead box, radioactive material in there, shooting out alpha particles, going through this thin sheet of gold. Most of the particles went straight through, landed back here. He was able to sense those because he had a film screen, a zinc sulfide film-like screen around. Most particles went straight through, but a lot of them got deflected at almost like a 90-degree angle. So what he came up with was our modern concept of what an atom looks like to some extent. Most of the atom is made of what? Empty space. That's why these particles can go straight through. But almost all the mass of the atom is where? In the nucleus.
Is there a reason that you chose gold?
Probably because gold was just available in thin sheets, so they use it to gild things with. That's probably why I chose gold, would be my guess. But again, most of the atom is space. Most of the mass, Rutherford concluded, is in this tightly packed, really massive, positively charged nucleus. And according to Rutherford, which we now know is wrong, the electrons orbited the nucleus like planets orbit a star. You still see those pictures in textbooks, right? Your textbook would still lead you to believe that that's the way it works, because that was Rutherford's model. There were some problems with his model, and that gets into the emission line spectrum things. He wasn't able to explain why certain atoms gave off all these different kinds of energy. It just didn't work with his model. So, first of all, there's Rutherford's model. Electrons orbiting a positively charged nucleus with some neutrons in there. But in 1913, Niels Bohr comes along. And he wanted to take Rutherford's model and be able to explain all the different emission spectrums.
Ask Rutherford real quick. Did he think all the electrons orbit at the same distance, level, whatever, or that they each had their own orbit?
I think he understood that there were different levels. I don't think he thought they were all in the same orbit now. But what Bohr wanted to do was explain the problems with the Rutherford model. And he was using quantum mechanics, which is sort of a new thing at this point in time. What's a quantum mean? Yeah, a discrete packet. What we mean by that is energy, light in particular. You can't get light energy in any size you want. Light comes in certain packs, right? You either get the 1 pack or the 2 pack or the 3 pack. You don't get a 1.5 pack of light or a 2.5 pack of light. You either get 1, 2, 3, 4. It comes in certain sizes, and that's called a quantum. Energy comes in certain size packets. Okay, Bohr, what he wanted to talk about were some problems, like we said, with Rutherford's model. Tried to explain it in terms of quantum mechanics, and here were some of his main ideas. Number one, that electrons can't emit light or electromagnetic radiation while in a given orbit or energy level. If they're orbiting where they're supposed to be, they don't give off energy. When do they give off energy? When they're moving between orbits. That was a new thing. It was Bohr's idea. Everybody in chemistry did like the flame test, right? Those things give off light because when you heat them up, what's happening? They jump to a higher level and then they do what? They jump back. And when they jump back, to be able to go back, they got to give off energy. That's what we're talking about here. That same thing, same idea. But Bohr was the first guy to explain it. Bohr also said that electrons can't remain in any arbitrary energy state. They have to be in a certain energy level. He's the guy that sort of formulated this energy level thing. There are energy levels around an atom, and each one of those energy levels is characterized by a certain amount of energy, a discrete quantum of energy. If you're in that level, you got this much energy. If you're in the next level, you got this much energy, and so on. Kind of already said number 3, that the electrons emit energy, they give it off when they make transitions from a higher energy state to a lower energy state. Where are the lower energy states at? Closer. Because as you get closer to the nucleus, if you're an electron, you're less free to what? Less free to move, because what's happening to you if you're closer to the nucleus? You're getting pulled on by the protons more, right? And the positive charge is holding on to your tire. So the further away you get, the easier it is for you to move, the more kinetic energy you will have. So if we talk about the ground states, what are we talking about? Closer to the nucleus, less energy, right? An excited state would be anything other than the ground state, right? Further away. To move an electron to an excited state, what do you got to do? Add energy. Which can be through heat, can be through light, different kinds of things can do that. Another idea of Bohr's was that the energy of a photon that's given off by an electron, the energy of that photon is equal to the energy difference between the two levels that it moves from. So if it moves from this level down to the next level, the energy in the light that it gives off is equal to the difference in the energy of those two levels. Does that make sense? That's why if you heat up, say, what element? Let's say you heat up potassium. What do you always get in a flame test? Anybody know? You get purple. Because when you heat up the potassium, it moves to a certain level. As it falls back, it gives off that same amount of energy every time, and that corresponds to purplish, pinkish light. All right. One of the things that caused Bohr to do this in the first place was hydrogen, what we call the line spectrum emission for hydrogen. Scientists knew that when you heated up hydrogen or electrified it, you got all these different types of emission states. And notice these are the energy levels and the energy associated with them. So for example, energy level 5, negative 5.4. Energy level 4, negative 0.85. It's the amount of energy in that state. But if something moved from, say, 3 down to 4, what was given off? If an electron moved from energy level 3 down to energy level 2, what did it give off? It gave off red light. But if it moved from 4 down to, say, 2, it gave off green. If it moved from 5 down to 2, it gave off blue. If it moved from 6 down to 2, it gave off purple. If it moved from 6 all the way down to 1, it's giving off some kind of UV light. These are all the different forms of light that are given off when electrons drop, when they go from an excited state down to the ground state. And notice the energy levels over here are given in what are called electron volts. It's just a small unit of energy, an electron volt. So these energies are the energies associated with each particular state. What Bohr was able to figure out was this equation that we see right here. The energy in joules for an emitted photon is given by this equation. Now, F stands for frequency. Initial energy minus final energy. H is something I hope you dealt with in Chem 2, or in AP Chem if you're in there. And that's what? Planck's constant. About quantum mechanics. Got some kind of weird units on it. Notice the units there. This is the value for Planck's constant, though. And the energies that we need, those are coming from that diagram. So when we need to get the energies, we're going to go back to this line emission diagram and look at the energy associated with each level. That's where the energies will come from. So get that equation written down and Planck's constant and all that. There's one other equation that you're going to need to know to work problems like the one we're about to do, and that's this equation. You should have seen that before, even in like regular chemistry. What does C stand for? Speed of light. What's that funny little upside down Y thing? That's lambda, and that stands for wavelength, and the F is frequency. Realize in some textbooks, instead of using F for frequency, what sometimes gets used? Yeah, sometimes mu, or it looks like a V in a lot of textbooks. Frequency, it may look like a V. So just be careful. I'm going to use F, but if you see something that looks like a V, it may very well be frequency that it's talking about. And here we're going to use F's. So it's the speed of light equals wavelength times frequency. Negative 34. Erase that mark so you can see. So we're about to look at a problem based on these equations. So it says, give the frequency and the wavelength of a photon emitted when an electron makes a transition in a hydrogen atom from level 5 to level 3. So let's first go back to that diagram and let's figure out what the energy values are at level 5 and level 3. So if we look at level 5, negative 0.54 is level 5. I'm going to write that down over here so that I remember it. And level 3, negative 1.51. Just reading those right off the chart. So we're looking for frequency. And remember that equation was frequency equals what? Yep, initial energy minus final energy. So what was our initial energy? Where do we start out at? we started out in level 5. And what was the energy in level 5? Negative 0.54, right? Minus the final energy, or yeah, minus that. So that's going to be 1.51, and it's minus a minus, right? And all that's over H, Planck's constant. I always mess up Planck's constant. Let me make sure I get it right. I'm just going to say 6.626 times 10 to the minus 34. So let's work that out. All right, are you guys getting 1.46 times 10 to the 33rd?
Yeah.
All right, and when you work that out, give me just a second here. Ah, missed something. This needs to be in joules to make this work. Let me back up. It would be a lot easier on our math if this energy difference was in joules. The SI unit of energy is the joule, right? What's a joule equal to?
Meter per second squared times a second.
Yeah. You guys. A Newton meter is one way we're going to put it. A Newton meter. Yeah, you had 50 seconds in there, but you're close. Newton meter. So we need to convert from electron volts to joules, and I've got to figure out what that conversion factor is. Give me just a second. I'm going to get out of here for just a second and get a conversion factor on that. That's one I don't have memorized. All right, I'm going to write this over here on the board. This is the one you need to know. 1 electron volt is a very, very small unit of energy. We're just going to say 1.602 times 10 to the negative 19th joules. So it's a very small unit of energy. So we'll go back to our PowerPoint. We'll convert that top. So negative 0.54 plus 1.51. That gives us 0.97 electron volts. And we know that 1 electron volt is the same as that many joules over there. 1.602 times 10 to the minus 19. So we convert that out. And we get 1.55 times 10 to the minus 19. So instead of putting the electron volts up here, try that again. That's supposed to erase. I guess we'll go over to the next slide and try to do it. So again, our energy difference, 1.55 times 10 to the minus 19 joules. And that's all divided by Planck's constant, which is 6.626 times 10 to the minus 34. Hey, how are you? Now, the units are going to be important here. This is where you need to pay attention to units. Remember, your units on Planck's constant are meters squared times kilograms over seconds. What did we say the units on the joule were? Newton meters. Let's take that out. Now, one thing that you can see is you can cancel one of these meters, right? And what Walker was trying to tell you a minute ago is that a Newton is actually, what again, Walker? Kilogram times a meter over a second squared. That's what a Newton is. So you probably can see you can cancel some more stuff out there, right? Cancel out the kilogram. Cancel out. Let's see, is that going to cancel? Yeah, one of those is going to cancel. And you're going to left with something per second. What's that unit? With something per second. You got nothing on top over seconds. What is that? It's a frequency unit. It's hertz. It's hertz. So this is coming out in hertz. So let's divide it out. 1.55 times 10 to the negative 19 divided by 6.626 times 10 to the negative 34. And we end up with 2.34 times 10 to the 14th. And that is in per second. We can write it like that. Or we can just say hertz. Either way. I'm going to show you one more thing, and then I need to go to a meeting here in a second, guys. So, one other thing that came along just a little bit later, a little bit more quantum mechanics stuff. An electron only transitions from lower to higher energy levels when it absorbs a photon with an energy value equal to the difference in those levels. So what we're saying, Emma told us a minute ago that when you heat up potassium, you always get what color? Purple. You can't heat up potassium and get red because the difference in the energy levels for potassium is equal to what color of light? Purple.
Reminder students, we have homeroom this morning.
So it won't go back and forth. Remember, energy occurs in certain size packs. And if you can't absorb the pack, you can't absorb the pack. You can take it or you don't. Potassium can only absorb certain size packs of light. And that's what we call it quantum. We've got one more kind of problem that I would like to get worked. I'm going to post this PowerPoint, by the way. It'll be on Edmodo. And the video will be up there too. I tell you what, I think since I have to go to this meeting, I think I'm going to stop there. Next time we'll go to 7:45. But today, I need to get to my meeting, so I'm going to stop.